Hello and welcome. In this video, we're going to be taking a look at limits and continuity of multivariable functions. Now, in a previous video, we took a look at multivariable functions such as z equals f of x, y. And as an example there, that's x and y as your input. That's a two-dimensional domain we're working in. And then you get z, which is this third dimension, and you end up with a surface in 3 dimensions. So the idea of limits, continuity, and discontinuity is going to look quite different when we start talking about surfaces. And we're going to extend these concepts even just beyond that into functions of multiple variables. So why don't we start off with what we know from single variable calculus. If you want to think about continuity for single variable functions, let's suppose we had a function y equals f of x. We know that a function is continuous at a point A when the limit of the function f of x as x approaches a is equal to the value of f of a itself. Approaching from the left and from the right, we should get the same value, and whatever that value is also equal to the value of f of a itself. Now we do have a couple different forms of discontinuities as well. We have a removable discontinuity, and that would mean the limit of f of x exists as x approaches a. So from the left and from the right, it seems that we end up with the same value for each of those one-sided limits. But a removable discontinuity is when f of a doesn't exist. So it doesn't actually fulfill the equation of what continuity at a point would need. So unfortunately, it doesn't satisfy the equation for continuity at that point A because the right-hand side, f of a, is an undefined value. It'd be really easy to just go and correct that by defining f of a as the value of that limit, and that's why we call it a removable discontinuity. As for a jump discontinuity, though, that's when we don't have the limit from both sides approaching a agreeing. The limit as x approaches a from the left may be different than the limit as x approaches a from the right. In this case, you can see from the left, our limit is approaching some sort of higher value, and the limit from the right is approaching some sort of lower value. And it doesn't really matter if f of a exists or not. The left-hand side of this equation for continuity doesn't exist, and therefore we call this a jump discontinuity. Now we also have something maybe called an infinite discontinuity. That's where we have an asymptote, but typically that would be considered a jump discontinuity as well. Now it's time to shift gears to multivariable functions. Now the trick for multivariable functions here is that we aren't just limited to 2 directions, from the left or from the right. Our domain is actually going to be multivariable. As an example, if we want to work as a function of 2 variables, maybe we have z equals f of x, y, and that will give us a surface. Here is the domain of that function, and that's represented here as some sort of set on the xy plane. That's our input, and for every one of these points, a, b, where f of a, b is defined, we have a z value, and that will be giving us a height, and that's a point on the surface. Now the trick here is if we want x and y to approach the point AB, we don't just have left and right. We can approach that point AB from any direction we like. From the left, from the right, from above or from below. We could approach that diagonally. We don't even have to approach that along a straight line. We can approach that point along any path we choose. So that's really going to change this concept of a limit. We need to tackle what a limit looks like in a multivariable function before we can start talking about continuity. So put continuity aside for a moment. The definition there actually isn't really that different for continuity at a point for a multivariable function, but limits themselves are a little bit more challenging. Let's take a look at the definition of a limit of a function of 2 variables specifically here. And then we can always extend that to more variables, and we have a very similar definition. Let's start off with f being a function of 2 variables, and let's say its domain D includes points arbitrarily close to some point AB, except possibly at AB itself. So that means that here I've got this shaded region D, and that would be like a region on the xy plane. Inside there is some point AB where the function f may or may not be defined at. But the function is defined for a regions of points surrounding AB. That's kind of represented here by this disk. Everything within that dashed circle is going to be in the domain of f. F is defined at every one of those points. But possibly f of AB does not exist. Well, with that in mind, we say that the limit of the function f of xy as xy approaches AB is equal to L. We say that to mean that f of xy can be made arbitrarily close to whatever that value L is, simply by just letting x and y be sufficiently close to the point AB. Essentially, just by shrinking the radius of this disk small enough, we should guarantee that every point within that disk is within some desired margin of error from that value L. We could make that margin of error as small as we like, and all we'd have to do is just make sure that this disk is small enough to ensure that we're within that little tolerance of the value capital L. Now we have a little more formal definition for basically saying the same thing. That means for every small little tolerance or error, why don't we use epsilon, that's always going to be a positive value, then there exists some small little tiny distance, we'll call that delta, and delta is also a positive number, essentially thinking about the radius of that disk, such that the error here, the difference between the function and the value L, is always going to be smaller than epsilon, so long as this distance, this radius, if you want to think about of that disk, is smaller than delta. We just make that little region get smaller and smaller until we guarantee that we are not any further away from the value L than epsilon. And this can be extended to functions as n variables if we want, x1, x2, all the way up to xn. Very similar definition, except as you can see here, the notation gets a little bit clunkier. Now we already have seen in single variable calculus that the limit from the left may not equal the limit from the right, in which case the limit doesn't exist. It gets a lot more tricky when all of a sudden you're working in this domain of more than one dimension and you can approach a point from multiple different paths. So let's take a look at a few examples, and in certain cases you'll see that limit laws kind of just work the same way that we had in single variable calculus, and you can evaluate a limit. And in some cases it looks like everything is totally fine unless you choose a very specific path and you end up with the limit not agreeing with other paths. So let's take a look at those. Let's start off with a fairly basic multivariable function here. In this case, let's let xy approach 0, 0. And the function that we have here, you can see it's actually just a function of x divided by a function of y. It's kind of like they're really separated nicely here. And you can imagine that, well, if I plug in x equals 0 and y equals 0 into this, it doesn't seem like there's much of an issue. Well, luckily, we have several limit laws that we can borrow from single variable calculus here, and we'll have a couple of theorems later on to help explain this. But if you remember, with limit laws, whenever we have a quotient, we can take the limit of the numerator and the limit of the denominator, and we can divide those two limits so long as this bottom limit is not equal to 0. So let's take a look at this top here. The numerator 3x plus 1 is simply a single variable function, so we can treat that as just being the limit as x approaches 0. We don't have to worry about y. And in the denominator, we have a function that only consists of y. We don't have to worry about x, so we can just take the limit as y approaches 0 in the denominator. And the numerator is just going to equal 1. But more importantly, we want to make sure that the denominator doesn't have a limit equal to 0. And luckily, it doesn't. We end up with the limit equaling 1/3. A fairly straightforward example, and we'll be able to talk about continuity of this function at the point 0, 0 in a little bit. But let's take a look at a function that's a little bit more challenging now. You can see here that we have a function of x and y in the numerator and a function of x and y in the denominator. In this case, you'll also notice that I can't just simply plug in 0, 0 for x and y because I'll have division by 0. But if you think back to single variable calculus, a lot of times if we end up with 0 in the numerator and 0 in the denominator, maybe there's a common factor that we can work with here. Now I've set this one up so you actually have 4 terms across the numerator, And you can do a little factoring by a method called factoring by grouping. It's quite possible that you haven't done that method in ages, but what you end up looking for is a common factor of the first two terms and a common factor of the last two terms. And then hopefully you see that there's a common factor from each of those factorings. But let's try it together. We're going to look at the x to the 4 and 3x squared terms and see what we can factor out of those two terms. And the best thing we can pull out of those two terms is an x squared, leaving us with an x squared plus 3. We're going to do the same thing with the second two terms, x squared, y squared, and 3y squared have a common factor of y squared. And we also see a factor of x squared plus 3 there. Now, since both of these terms have a common factor of x squared plus 3, then we can factor one more time, leaving us with x squared plus y squared multiplied by a common factor of x squared plus 3. That should allow us to rewrite this quotient as something that has a common factor in the numerator and a common factor in the denominator. Now that we see that these two rational expressions are equivalent, we may have to remember another good limit law from single variable calculus, that the original limit is actually equal to the limit of this new function as x and y approach 0, 0, because these two functions are equal for all of R2, except for this one point where the denominator equals 0, when x squared plus y squared equals 0. And that's only a single point. That equation only has one solution. That is the point x, y equals 0, 0. So essentially what we're saying is that these two functions, one in blue and the one in red, are exactly the same in an entire region of R2 around the point 0, 0, except at the point 0, 0 itself. So that means that they should have exactly the same limit, with the benefit that this new function in red, we can just simply simplify by canceling a common factor. We're going to get rid of this x squared plus y squared in the numerator and in the denominator, and that just leaves us with the limit of x plus 3 as x and y go to 0, 0, and that gives us the value 3. That only works in this case just because these two functions are exactly the same everywhere around the point 0, 0. All right, well, let's do one more example, and this one's going to be a little more challenging. This one, you really have to keep in mind the idea of a limit only exists if it's the same value along multiple paths. Here, let's take a look at the limit, again, as x and y go to the origin 0, 0. This time we're looking at the function 3xy all over x squared plus y squared. Now, at first glance, it's kind of similar to the last example, but there may not be exactly an obvious way to simplify this expression in order to be able to plug in that point 0, 0. So instead, let's think about different paths that we can take in order to get to that origin 0, 0. Let's start off with an easy way to get to the origin and simply travel along the x-axis. If we're traveling along the x-axis, then that would mean that our y coordinates will equal 0 and our x coordinates are going to approach 0. And we can do that from the left and from the right at the same time. The nice thing about that is that essentially what we get to do is we take the limit that we were given and we can replace all of the y's by 0 along that path. At that point in time, we simply just need to take the limit as x goes to 0, and we're back to a single variable limit. And we can see here that no matter what x is, as long as x is not 0, as we get closer to 0, this just evaluates to 0. So at first glance, it appears that this limit may equal 0. But of course, let's try some other paths to make sure that we end up with 0 from every direction. Let's try going along the y-axis. In this case, our x is going to equal 0, and we're going to let y approach 0. So we can take the original limit. We can substitute x equals 0. That gives us 0 in the numerator. And then we just have to evaluate the limit as y approaches 0. And once again, this gives us 0. So this starts kind of confirming our hypothesis that maybe this limit does equal 0. But those are really just the most convenient ways we can possibly approach the origin. We've looked at from the left and from the right, from above and from below. Why don't we start at least looking at some sort of diagonal line? An easy choice here would be along the line y equals x. So we're going to make that substitution, y equals x, into the original equation. And then we simply just need to let x approach 0. Let's see what that looks like. Here we're going to replace all of the y's with x, since we're along the line y equals x. That makes this a single variable limit. And then along that line, we just need to let x approach 0, either from the left or from the right. And we can simplify that down and see whether or not this limit equals 0 again. That gives us 3x squared over 2x squared. And then unfortunately, that can be reduced and the x's can cancel. That leaves us with 3 over 2. So it's at this point in time that multiple paths come up with different values of the limit, and we already know that this limit doesn't exist. And that would be a sufficient proof right there to show that this limit doesn't exist. But let me show you at least maybe a couple other creative ways so that you can take any diagonal path all at the same time. If we wanted any line through the origin, and we don't care what slope it is, we could just choose a line y equals mx. So that way we know it is going to pass the origin. And we'll just let x approach 0. And this is very similar. If we were to go and walk through all the steps here again, we're going to replace y with m times x. That gives us 3mx squared in the numerator, and then we'll have x squared plus mx all squared, and well, we can factor an x squared at the bottom. That gives us m squared plus 1 times x squared. And now that we only have x as our variable, we take the limit as x approaches 0, and x squareds cancel. We end up with 3m over m squared plus 1. And since x has been canceled, and this is just constant, this limit equals 3m over m squared plus 1. The big thing here to realize is that if we plug in different values of m, we end up with different values of the limit. And because that depends on m and it's not path independent, this limit doesn't exist. Now, another option that you have here, instead of thinking about lines through the origin, is the origin is very convenient in polar coordinates. It's also just 0, 0. And if you want to approach 0, 0 from various different angles, then why don't we just switch to polar coordinates? In which case, we can let theta be anything we want, and we just need r to approach 0. And that will also ensure that we get towards the origin, but from any direction we like. Remember that when we want to switch to polar coordinates, we have a few conversion formulas. X equals r cosine theta, y equals r sine theta, plus x squared plus y squared equals r squared, and tangent theta equals y over x. And if you've forgotten those at any point in time, it's pretty easy to draw a little right angle triangle with x, y, r, and theta labeled on there. Now in this case, if we're trying to get towards the origin for x and y, that just means we need r to approach 0. And if we want any possible angle, then we can let theta be any angle from 0 to 2 pi. Using some of those little substitutions, we'll take our original limit and we'll replace x with r cosine theta and y with r sine theta. And in the denominator, we can see that we have x squared plus y squared, which just becomes r squared. And now we don't really care what theta is. That allows us to use any angle at all. We just need r to approach 0. And we can simplify. We have r squared in the numerator and r squared in the denominator. That leaves us with 2 sine theta cosine theta. And since r is no longer in this expression, this is constant with respect to r. In fact, that just ends up equaling the value 2 sine theta cosine theta. Or if you prefer using an identity, we can actually write this as sine 2 theta. And once again, just like that line through the origin y equal mx, this depends on the angle. Not depending on slope like in the last example with m, this depends on what angle theta we choose. If you want to plug in various different angles theta between 0 and 2 pi, you should see that this limit will come up with different values, so the limit does not exist. Any one of these various different paths would be sufficient for showing that the limit does not exist. We simply just need to find a way to show that coming from different paths, this limit would end up equaling different values, which is impossible. Now, what can be a little bit more challenging is if a limit does exist and you cannot seem to find an additional path, how do you prove that the limit does in fact equal some value? Well, oftentimes that involves using the epsilon and delta definition of the limit. Now, I will mention that just because you've tried multiple different paths and all of them seem to agree on the same value, that doesn't necessarily mean that the limit does exist. sometimes you have to get a little bit more creative and you can still show that the limit doesn't exist. Here we basically have tried approaching the origin along straight lines, along the x-axis, y-axis, a diagonal line, and then using polar coordinates, which also just approaches along a constant angle. But if you're looking at a limit, let's say as x and y approach the origin 0, 0, you could approach the origin along a parabola. You can approach the origin along the curve y equal x squared if you want. You could approach the origin along path x equals the square root of y if you wanted, as long as y is only going to be approaching 0 from the positive side. There are quite a few options. Think of any curve that passes through the origin, and you could potentially make a substitution into the expression so that you're approaching along that specific path, and then turn it into a single variable limit and see if you still come out with the same value. And if you're always coming out with the same value, then there's maybe a little better chance that the limit does exist, in which case the epsilon delta sort of argument is probably the best way to go to prove that the limit does in fact exist. Well, now that we've talked about limits, now we can come back to the idea of continuity and what a discontinuity looks like for a function of multiple variables. Now, much like the definition of continuity at some value for a single variable function, here's a function of two variables, f of x, y, and we would say it's continuous at a point a, b if the limit of the function f of x, y as x and y approach the point a, b is equal to the value of f of a, b itself. And there's a few takeaways from that. First of all, this implies that f of a, b is defined. Maybe that makes a lot of sense. A function is not going to be continuous at a point where it's not defined. But secondly, this also implies that that limit on the left-hand side of the equation exists. And we've just seen that that only can happen if you end up with the same value from all directions or along any path you choose. So if the limit on the left-hand side does not exist, well, it can never equal the value on the right-hand side. And last but not least, the value of f of a and b must be equal to the value of the limit. That's really what this is saying. Step 3 is making sure that both of those values are the same. Even if they both exist, they don't necessarily have to be equal. Now, luckily, we have a few theorems so that we can show that a function is continuous at a point in a little bit easier way than just using the definition. In this first theorem here, we're going to start off with just two single variable functions, g and h. And let's use different variables, g of x and h of y. G of x is continuous at x equals a, h of y is continuous at y equals b. Well, combining those two functions together will create a multivariable function, a function of two variables in this case, and this function is going to be continuous at the point a comma b. We can combine the two functions together with addition or subtraction, multiplication, or division. And we'll still end up with a function that's continuous at x equals a and y equals b, so long as we don't end up causing division by 0 when we combine the functions. So in C here, by plugging y equals b into this denominator, as long as it doesn't equal 0, then the combined function g over h would be continuous. And here in D, making sure that when we plug in x equals a in the denominator, we shouldn't get 0 there either. So that first theorem is a great way to create a new continuous function out of single variable continuous functions. Now, for this second theorem, we'll start off with two multivariable functions. In this case, functions of two variables. F and g, let's say, are functions of x and y, and they are both continuous at a point a, b. Well, combining f and g together will also create a new continuous function at that same point. F plus g, f minus g, f times g, and f divided by g will all be continuous at that same point, so long as the denominator doesn't equal 0 in the case of f over g. So why don't we go back to some of those functions that we looked at earlier in limits and see whether or not they are also continuous at that same point. In our first limit example, we looked at the function 3x plus 1 over cosine y plus 2. And the numerator is a single variable function, a function of just x on its own, and the denominator is a single variable function, a function of just y on its own. We know that the top is a polynomial and it's continuous for all real numbers. And we know that the denominator is a trigonometric function, cosine y, just shifted up 2 units, and that's continuous at every real number. So that would mean that this function is continuous over all of R2. X and y can both be any real number we like. The only thing we would have to potentially check is to see where cosine y plus 2 would maybe equal 0. But trying to solve that equation would mean that cosine y would have to equal -2, and that's never going to happen. So that means that this function is continuous over all of R2. But don't ever forget that we sometimes have to take a look at that denominator and just see if it could potentially equal 0. At those points, then we would have a form of discontinuity. Now in our second limit example, we looked at the function f of xy equals x to the 4 plus 3x squared plus x squared y squared plus 3y squared all over x squared plus y squared. Now, this time around we have a polynomial in the numerator, but of 2 variables in x and y. Now, luckily, as a polynomial, it would be continuous, in this case, over all of R2. And in the denominator, we also have a polynomial, and that would be continuous over all of R2 as well. Unfortunately, we just have to make sure that the denominator is not equal to 0. And the polynomial in the denominator, x squared plus y squared, is only going to equal 0 at a single point, 0, 0. So this function is going to have a discontinuity at that point, 0, 0. However, we did find that the limit of this function as xy approaches the origin does exist. And we'll see maybe what kind of discontinuity that is. In this case, we know that the limit of the function as xy approaches 0, 0 was equal to 3, but it's not continuous because f of the origin does not exist. In our final limit example, we looked at the function 2xy over x squared plus y squared. Now, once again, we have a polynomial in x and y over a polynomial in x and y. So it would be continuous over all of R2, except for this one point where the denominator equals 0. And that, again, is the origin. Now, we actually found that taking various different paths towards the origin led us to different potential values for this limit, which is impossible. We would just simply have to say that the limit does not exist. Well, now that we've taken a look at what it means to maybe be continuous or discontinuous at a point, let's see if we can actually visualize these surfaces and see what those discontinuities look like. So over here in Maple, I've got a few commands to take a look at. With plots is just so that we can use 3D plotting tools. And I'm going to plot each of these 3 functions over the domain of x from -2 to 2 and y from -2 to 2, just over that square around the origin. Now the first one here, 3x plus 1 over cosine y plus 2, is continuous over all R2. And if you take a look at it, it's a nice smooth surface. And you might be able to see how there is a little bit of some kind of cosine curve going there. It's part of one anyways. You can see how it has a little bit of that oscillation that a cosine graph would have. But of course, that's in the denominator, so it does some pretty strange behavior. 3x plus 1 in the numerator is also going to be largely what defines the shape of this. Anyway, you can get a good sense of what that would look like, and the origin right there in the middle, it's definitely continuous at that point. Now this next surface has a discontinuity at 0, 0, but the limit as x and y approach 0 did exist. And after factoring and canceling common factors, we end up showing that this is equivalent to the graph of x squared plus 3. That's a parabolic cylinder, and that's exactly what we have here. It's basically that shape of x squared plus 3. Here's the actual sideways graph of z equals x squared plus 3. So the only thing is that Maple has a bit of a tough time with this one spot in the middle at 0, 0. You can see it really struggles to figure out what to do with that spot. It's kind of like somebody just punched a hole in the middle of the surface. And this is essentially analogous to the removable discontinuity. We could simply just patch that hole and it would be a nice smooth surface, not a problem. Now, in our last example, we have another function that is not continuous at the origin, but this time the limit didn't exist. And it gets to be a pretty strange looking surface. So you can see that this is a surface and it looks pretty smooth except for this one very strange area. Again, Maple has a tough time trying to graph that. And taking a look along the x-axis here, well, if we're looking straight down, that would be sort of this line here, right at y equals 0. If we're going to approach along that line, you can see that it looks like the limit should equal a z value of 0 from left and from right. Along the y-axis, that would be where x is equal to 0. And you can see that that agrees. But if you're coming in from a diagonal, down at this bottom of this trough here, if you're staying along the bottom, it looks like you're going to end up hitting maybe a z value of -1. Or if you're heading along this diagonal across the ridge, it looks like you're going to approach a z value of +1. And taking a look at all of these different approach paths, you can see that they don't all agree. So this is what it looks like to have the limit being different from different paths. And this is not a function that we can easily fix. Unlike this parabolic surface with just a tiny little hole in it, this one here has been pinched and it's basically not salvageable by just a little patch job. This is kind of analogous to like a jump discontinuity in single variable calculus. Now, hopefully that visualization kind of helps explain what limits look like along a surface and gives you an idea of what kind of continuity versus discontinuity a surface could potentially have at a given point. Now, all of this can be extended even further into functions of more than 2 variables, but it gets very difficult to visualize it. And the idea of taking many different paths in more than just 2 dimensions also gets a little bit tougher to visualize. But hopefully you can kind of see how all of the theory from single variable calculus with limits and continuity just extends upwards into multivariable functions. So we'll take a look at this in the future because you know this is probably leading to a very important definition, which is going to be our derivative. That's kind of what we use limits for, first of all, in single variable calculus. So stay tuned. Thanks for watching, and I'll see you in the next video.